All right, now let's move on to magnetism. So, to begin, we're just going to talk about this object known as the magnetic field. So, we know that stationary charges generate electric fields, which can influence the motion of other charged particles. But also, it turns out moving charges are sources of a new field called the magnetic field. Now, if you really look at it, these two fields are intertwined due to special relativity effects, but we're going to consider these effects as separate for now. So, you might think that we'd call the magnetic field M for magnetism, but of course, M means so many other things. We actually call magnetic field B, and this is more for historical reasons. So you'll hear the term B field used interchangeably with magnetic field. It came up when Maxwell's equations were being compiled. So, this object, the magnetic field, we're not really talking about what it does yet. We're really just looking at its properties today. Magnetic field is measured in a unit known as a Tesla. The Tesla has a very strange definition if we look at what it's equivalent to in other unit systems. But magnetic field, typical orders of magnitude are small. Many of our magnetic fields will be micro Tesla. Even the largest MRI machines are going to be in the single and double digit Tesla numbers. And those MRI machines can drag metal chairs across a room. So a Tesla is a very strong field. So, where does magnetism come from? Well, at some point, we need to accept that it is just a property of our universe. So, just like fundamental particles have mass and charge that we've accepted, each particle also possesses a magnetic moment. So, this means that all these little particles are really just tiny magnets. And we model electrons as moving very quickly, so these tiny magnets moving around can generate a field. Now, of course, that sort of breaks down when we look at the quantum model of the atom, and we have to be a bit more creative in our analogies, but we can say that all these little particles carry their own little tiny magnets with them. So this relates to something known as spin. We're not getting into that, but the classic analogy says to imagine what spin is. Imagine a spinning ball, except it's not a ball and it doesn't spin. It's really just this quantum effect. But really, this relates to chemistry, that when filling electron orbitals, the spins begin to pair off. And you can think of these as these magnetic effects that will start to cancel out. So if a material is strongly magnetic, it's going to have all of its tiny magnets sort of agreeing with each other. So this would be an atom that is a candidate for being magnetic. Because yes, one of its orbital shells has those canceling tiny magnets. But as we fill its second shell, its spins are unpaired, so it's a candidate for magnetism. Whereas if we look over here, we have paired spins where all these tiny magnets are going to be of opposite orientations. And that alone actually doesn't make us have a magnetic material. This is just the first step. So even though the magnetic moments of groups of particles also need to align, it's very rare for a material to be magnetic at room temperature. So due to material properties, most magnetic domains end up canceling out, and our exceptions are iron, cobalt, and nickel, which are our ferromagnetic elements. And if you want to think of what a very strong magnet is, think of iron for ferro, right? Fe. So what we mean by magnetic domains is if you think of a chunk of material, on average, all the chunks will be magnetic, but the magnetic chunks will tend to cancel each other out, right? I can pair off these chunks and cancel them. But in a magnet, it just so happens that as the material formed, its domains happen to perfectly align. So this would be what a permanent magnet looks like. These aligned domains. So the ability for a material to become magnetized is called the magnetic permeability, mu, which is the magnetic version of permittivity, epsilon, where we said epsilon was how easy it was for E fields to sort of polarize a material. Permeability is how easy it is for magnetic fields to become stronger in a material. So now we have a vocabulary lesson here. The strongest level of magnet you can get is ferromagnetic. So ferromagnetic materials, they strongly align their domains to match the direction of the applied magnetic fields. I've called these your sheep of the magnetic world. You tell them to align one way, and they will. And even after you remove the field, they continue pointing in the way that the field told them to point because nobody else said think differently. And these are only your best of the best materials. So iron, cobalt, and nickel are your metals at room temperature that exhibit ferromagnetism. Paramagnetic is the next level. So it only slightly aligns the domains. So people have described this as sort of an orbiter, where they're going to think their own way, but if somebody comes along that they're trying to impress, they'll change their opinion to match the person around them. And as such, they're only pretending to agree. So as soon as the magnetic field is removed, in a paramagnetic material, the domains go back to normal. Diamagnetic is sort of outside the scope of AP, but there's also a small element of opposing the direction of applied magnetic field. Think about this like how in a dielectric, the polarization works to cancel out the E field. But we're really only going to look at paramagnetism and ferromagnetism. So this is a vocabulary thing. And just think that word ferro, you think about iron, so it's a really good magnet. So we have this random sample of magnetic domains here. And we're going to apply an external magnetic field to this that points towards the top of the page. And notice I called it B because it's a magnetic field and that's our symbol. So what could this material look like if it's a ferromagnet? Well, if it's a ferromagnet, that's your sheep of the world. So these domains are going to quickly align upwards. And we're going to approximate that it's perfect. So ferromagnetic is strongly aligned. Paramagnetic, however, yeah, they'll change their mind a little bit, so they're kind of influenced. So you could definitely tell it's up. There's a little bit of canceling happening, but it's kind of weakly aligned or slightly aligned. What happens in each case if we remove the field, though? Well, if you have a ferromagnet, absolutely nothing. Because ferromagnets, you have to tell them to behave differently. They're the sheep. They don't know how to think for themselves. So we call these your permanent magnets. Because even when you remove the external field, unless if you bring a new one, it's going to continue with that alignment. But the paramagnetic, these are your fake people. So the magnetic moments return to their original orientation. So you don't get a magnet anymore. So that's why ferromagnetic is a stronger or permanent magnet, because it persists. The magnetic field persists being aligned even after you remove external fields for ferromagnets, but paramagnetics do not. And then for a little extension to fill the page here, an inductor is a circuit element that can store energy in magnetic fields. An inductor is constructed using a coil of wire that contains a solid core. So this is going to be like a slinky. Imagine a slinky with a core inside. So if we're trying to make these inductors that are really, really good at storing energy in magnetic fields, would we want a ferromagnet or a diamagnet inside? Well, this diamagnetic is kind of a weird word where it cancels the magnetic field. And if the entire goal is to store energy in magnetic fields, we want to make our magnetic field as strong as possible. And by definition, if we put a ferromagnet inside the core of this inductor, it's going to have a very high permeability, which strengthens the field inside that material. So energy can be stored inside E and B fields. To maximize the strength of the magnetic field inside, a ferromagnetic material should be used. because this means the magnetic domains in the material are going to align with the field, increasing its strength. So what we mean by this is we create this object known as an inductor. This is definitely just looking like a spring. Think of a spring or a slinky. And it's saying that what we can do is if we want to strengthen the field inside of it, we can actually insert sort of an iron core or an iron rod inside this coil that's going to make the field stronger. All right, now we have the lab on para and ferromagnetism. A group of students find a nail of unknown metal in the lab. How exciting. They wish to use a bar magnet and paper clips in order to determine whether the nail is ferromagnetic or paramagnetic. So this lab isn't calculate, it's which one of these two is it. So there's really one way to do this, I feel. So remember that both of these are going to become magnetized. So we're assuming that if you rub the bar magnet on the nail, it's going to become magnetized. That doesn't tell you much. But what does tell you which of these two it is how it behaves once you get rid of the bar magnet. So we're really just seeing, like, you know it's going to be one of the two if you rub the nail with the bar magnet and it picks stuff up while the bar magnet is attached. But to really test if it's ferro or paramagnetic, you want to see if it is a permanent magnet or a temporary magnet, right? So ferromagnetic is permanent and paramagnetic would be temporary. So it's pretty straightforward. Ensure that the nail is attracted to the magnet, rub the magnet against the nail, then move the bar magnet far away and see if even when the bar magnet is far away, does that nail keep its magnetization? So we have this lovely diagram where we rub the nail against a bar magnet and we test if these paper clips are attracted or not. What a lovely diagram. This is actually some of my better work. So, is it ferromagnetic or paramagnetic? Well, if the nail remains magnetized, even when the bar magnet is removed, it's ferromagnetic. If the nail fails to be magnetic, once the bar magnet's far away, it's paramagnetic. Assuming, of course, it could be magnetized in the first place, right? Because we have permanent magnet or temporary. Pretty straightforward there. So now let's talk about some properties of this magnetic field. So this is something that is not the same as electric fields. So electric fields, you can have positive charges, you can have negative charges, but you can't actually have what's called a monopole for magnetism. So all static sources of magnetic fields have two poles, a north pole, which can be thought of as a source of magnetic field lines outside the magnet, and a south pole, which is a sink. So notice this looks very similar to a dipole electric field where we have like a positive source and a negative sink. There is a slight difference we'll talk about later. Now, okay, cool. All magnets have a north and south pole. But you're probably thinking that, can't we just get around this rule? I have a north and south pole. Why don't I just cut this in half, right? If I cut this in half, won't I just get a source and not a sink? Well, it actually doesn't work that way. So all magnetic field lines always form closed loops. So actually breaking a magnet doesn't isolate the north and south. It actually just creates two smaller bar magnets. So this is just a property. This is just how magnets behave. We have been searching for monopoles forever and have yet to find them. So this is a property of our universe, that you cannot isolate a magnet pole like you could with a positive charge or a negative charge. So these are our two sort of main properties. So the main one is that all magnetic field lines form closed loops. So every single field line you trace must loop in on itself. So that shows there's going to be some weird stuff happening inside the magnet. And our other rule is that outside magnets, north poles are sources and south poles are sinks. So now we'll introduce a kind of abstract concept. This will become useful to us in the calculus unit, but we're going to define this idea of magnetic flux. And flux is really close to the word flow. So we want to say that flux is like flow. So the flux, given the Greek letter phi, is the net flow of anything into or out of a surface. So how much light is coming through your window every second? So we're going to talk about electric and magnetic flux in this class. And today in particular, we're going to talk about magnetic flux, which talks about how many field lines are entering or exiting your surface on average. If a field line exits the surface, we say that that is positive flux, and if it enters the surface, we say that's negative flux. And this only applies to 3D surfaces where there's a well-defined in and out. So we mean things like spheres and pyramids and cubes, where there's a clear distinction between what's called inside and what's outside. Because if you have like a circle, it's not as clear. So this is our definition of how to calculate flux. It's the amount of a field that pierces an area. So it's important that we actually look at this perpendicular part. So it isn't just field times area, it's actually the perpendicular component of the field times the area. And what that means is that if you have like a 2D surface and you have a field that's piercing at an angle like this, notice that all of the field isn't necessarily piercing the area. So you'd actually have to extract this part using a sine or cosine to extract the actual perpendicular, or the penetrator component, as we've been calling it. So as a result of the fact that every magnetic field line loops in on itself, there's actually one of our first of 4 Maxwell equations, which is one of the 4 rules that governs all of E and M. And Gauss's law for magnetism states that if you have a closed surface, so this means a surface with an inside and an out, like a sphere or a cube, you can never have a net flow into or out of the surface. And that should make sense, because if you have a 3D surface and every field line loops in on itself, any field line that goes in must also pass out. So there's no net flow. This does not apply to 2D shapes because there's no in and out of a 2D shape. So usually we just say flux is always positive if there's a 2D shape, because there's not really an in and an out. So again, just to model what this looks like, I'll just draw one field line because it will probably make more sense. If we draw ourselves a sphere, or just any shape, it doesn't actually matter what. Maybe we'll scoot this bar magnet a bit closer so I don't have to draw some crazy field lines. Notice that if I draw a field line that enters this sphere, we know it can't just like hang out in the sphere, because we know that these field lines form closed loops. So because it forms a closed loop, we know it's got to pop out. So notice that, yeah, the field line entered the sphere, but it also left. Same thing, we could draw a different field line and it does a similar thing. So Gauss's law for magnetism says that the net magnetic flux is 0, because this is a sphere with an in and an out. If I put it right next to a flat square, different story. So what this equation encodes, this just encodes the fact that magnetic field lines loop in on each other. So you can't just lose a field line somewhere. So let's consider the magnetic field generated by a bar magnet. So first we want to draw 4 example field lines on this figure outside the magnet. So this will take me a minute usually not. This is one of my weakest areas. We always know I'm bad at artistry, but this is my weakest of the week, is drawing magnetic field lines. So we are roughly going to say that north poles are sources of field lines and south poles are sinks. So I could draw a line there. Okay, we're actually not doing terrible. Not doing terrible yet. There's some field lines, and then here's where it starts to get a bit dicey. We can draw an even bigger field line. You know what? I will take that. I will take that. First try. That is not terrible. So it says draw a closed surface anywhere on the figure above and verify Gauss's law holds. So I'm just going to draw a cylinder, maybe right up here. So this is going to be what's called a Gaussian surface. This is our name for fake surfaces we draw to illustrate something. So we want to verify Gauss's law holds. So what does Gauss's law say? Gauss's law is about the net flux. So what is the net flux? Well, the net flux would be proportional to field lines that are exiting the surface minus the field lines in. Because we said that outward flux is positive. Think about it like electric fields where positive charges would generate sources, so there'd be outward flow. So let's just count. How many field lines enter the cylinder? Well, the field lines are entering right here. And notice I count 1, 2 field lines. Oh, sorry, that's in. That's in, so we'll put that over here. All right, so our negative flux would be entering that surface. And then what about exiting? Well, exiting would be this one. And how many field lines exit? Well, I count 1, 2 field lines popping out this other side. So there's 2 lines out. So 2 minus 2 equals 0. So we see that the net flux equals 0 as expected. Because since these field lines form closed loops, they can't just vanish inside the surface. They have to pop back out somewhere. Now, I know we didn't really do this precisely. This is more of a qualitative example. So let's draw an open surface and verify that this does not follow the rule. So what is an open surface? Well, an open surface is just a one-sided shape, or it's just a surface without an in and an out. This is just a random circle. So what is in? What is out? I don't know, but I can clearly tell that 2 lines are piercing this surface. So notice that the net flux through the open surface is equal to 2 lines, and notice that is not equal to 0. So if you draw a surface that just has one side, this is called an open surface because there's not an inside to it. It's not enclosing a volume. So that's the distinction. A closed surface has volume. An open surface would only have like an area. So does not hold. Now this is weird. What's going to happen to the field inside the bar magnet? Because we haven't looked at that yet. Well, we do know they form closed loops. So I'm just going to close all my loops inside, and then we'll deal with the direction. All right, well, notice if I trace one of my field lines, I see that it exits the North Pole, travels this way, travels this way, travels this way. So it's actually got a reverse direction inside. So inside the bar magnet, counterintuitively, it actually points south to north. So I said there's a big difference between this and the dipole field for electric fields, and this is it. So since these field lines loop into each other, we actually get the field direction reverses. It goes from south to north inside the magnet. And that's opposite our model of sources and sinks. So the sources and sinks works outside the magnet, but it reverses inside because what takes priority is the closed loops rule that defines a magnetic field. So kind of interesting there. Notice you need that to enforce the Gauss's law property inside the magnet. Consider the following vector field. Suppose the vectors are an electric field. Describe a charge contribution that could generate this field. Justify your answer. Well, I hope we all know what electric field this could be at this point. This certainly looks like a positive charge to me, right? Positive charges are sources of electric field lines. So what charge distribution could generate this? Well, I could have just drawn a positive charge, and this totally works. And I'm also not drawing the worst radial field of my life. What kind of cooking today? Maybe besides this line. So this could totally be an electric field. Could be a positive charge just hanging out. That's not illegal. Positive charges can live by themselves. Could it be a magnetic field, though? Well, here's where we can use some clever thinking with Gauss's law. So, notice, Gauss's law says that if I draw any 3D surface I could possibly think of, I need to get zero flux through it. So if I drew this magical sphere, that was centered at the center of this diagram, notice the flux is definitely not zero through this sphere. And this sphere is a closed surface, right? So why is the flux not zero? Well, I see out, 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 out. There are no field lines that enter this surface. So the flux is strictly positive. So it can definitely not be a magnetic field because these don't loop in on each other. So there's actually a Gauss's law for electric fields that's much more useful to us for problem solving. And it turns out that the flux due to electric fields need not be zero. And we're really interested in that. Because, yeah, you can totally just have positive charge by themselves, and that'll generate flux. So that's totally fine for an electric field, but can't be magnetic, because magnetic fields have the looping in on each other property. And now we have kind of a funky example of Gauss's law, where we have this cup shape. I've been informed that this might be called a frustrum, something like that. This is a cone with like the top snipped off. So the shape is placed in a uniform B field of 5 microteslas that points straight up, and it's perpendicular to each circular face, so there's no weird trigonometry to do. And what we want to do is calculate the flux with sign through all faces. So notice that this is a 3D shape because there is a clear volume inside the cup. I can fill this with liquid. So if the field enters the cup at a surface, we're going to call that positive, or say negative, because it's a sink. And if it exits, it's positive. All right, so let's do that. Calculate the magnetic flux, including sign, through each of the following sides. Bottom face, top face, barrel. Right? We can split this shape into 3 surfaces. The bottom circle, the top circle, and everything else, which I've called the barrel. All right. So just roughly drawing my circles here. Okay, that's not the worst in the world. So now we'll save that. Yeah, I will say doing this in one take without having to reset for drawings, some of my better work. Okay, bottom circular face. So that means we have this 5 microtesla field. Which pierces this area. So maybe I should actually color the area first. So we're looking at the field that's piercing this area. Well, flux, remember that is equal to B perpendicular times A. And all the field is perpendicular here. So we can just easily calculate that phi through the bottom is equal to the 5 microtesla times the area of the bottom face. And this is 2 meters. Wow, this is a giant cup. This is 2 meters. So the area of that would be pi times 2 squared square meters. And also we have to account for the fact that this is an inward flux or a sink. So since they're going in, we'll also tack on a minus sign. And I'm not going to compute the actual decimal here because it'll help us later. 2 squared is 4. 4 times 5 is 20. So we get negative 20 microtesla meters squared. 20 pi. So we have that amount of flux that enters the bottom. All right, what about the top? Well, the top is going to be equivalent. There's just a different radius. So what is going on in the top? Well, it's the same field. It's, of course, the same field, except now we're getting an exit. So phi through the top is equal to positive 5 microtesla times pi times the upper radius is 1. So here we get positive 5 pi microtesla meters squared. So we got 20 pi in and 5 pi out. Flux is a scalar, but it is a signed scalar. And last we got the barrel, which is this sort of like, it's these sort of edges. So we can't just, well, also I don't even know the area of the barrel, so that's not helpful. So there must be another way, and there is. Because what does Gauss's law say? Gauss's law says there can be no flux, there can be no net flux in or out of this cup. So Gauss's law says that the net flux must be 0, because magnetic field lines must loop in on themselves. So what is the net flux? Well, the flux through the bottom plus the flux through the top plus the flux through the barrel must eventually cancel if I take all the surfaces. So what's the flux through the bottom was negative 20 pi. The flux through the top was 5 pi. And I don't know the flux through the barrel. So, of course, we can solve this, and I have to scoot this a little bit, and we're going to shrink it so I have space. So we can see that phi through the barrel must be, well, negative 20 and positive 5 make negative 15, so I need positive 15 microtesla meters squared. So we had to use Gauss's law to reverse engineer this, because we knew the flux through 2 of the 3 surfaces that make up this shape, so the third flux had to be whatever was necessary to cancel out the flow. And it makes sense, because there was much more flow into the bottom than there was out of the top. So there must have been a bunch of extra flow out the sides. Oh, 5. There's a pi, of course. And the pi has always been there, I promise. I'm not gaslighting you. There we go. Yeah, so that's our basics of the magnetic field. So now we're actually going to talk about how this affects the motion of particles.